What can outshine the sun? No, not just the sun, but entire galaxies, even our Milky Way. Is there an object that spins faster than your favorite smoothie blender? Maybe not on Earth, but in the vast expanse of our universe, there exist two powerful yet mysterious phenomena that push the limits of physics. Objects that radiate the energy and light of 500 trillion suns and spin up to 1,100 times in just 1 second. They are quasars and pulsars. Quasars and pulsars are high-energy objects in our universe formed due to catastrophic and extremely violent events in the universe, possibly the most powerful of such events ever known to man. Astronomers have been fascinated by events beyond the skies for centuries, and man's persistent curiosity led to the discovery of both phenomena in the 1960s. With this discovery, scientists have gained more insight into the nature of the universe, unraveling its deepest secrets to see our place within it. As we continue to study these mind-boggling objects, we can learn about the cosmic space and how well it conforms to the fundamental laws of physics. By that, we mean the behavior of matter in the deep corners of the universe, the nature of dark matter, and so much more. Now, what exactly is so intriguing about quasars and pulsars? Before we get into that, let's talk about an interesting science-driven innovation. Are you a content creator looking to enhance your creative efficiency? 11 Labs voice cloning service is for you. Imagine being able to translate your content into any language you want without changing your voice, or switching accents to help your target audience understand you better. 11 Labs offers all these and more. Explore all its offerings using the link in the description. The name quasar comes from the expression quasi-stellar, meaning star-like. These objects are generally termed luminous active galactic nuclei, AGN, which just means that their luminosity is not derived from stars. Quasars are extremely luminous objects, commonly described as the bright cores of active galaxies. The core of an active galaxy is embedded right at its center, making it super bright. Unlike the typical galaxy, these active galaxies also radiate way more energy than others. The energy is found in the infrared, radio, ultraviolet, and X-ray regions of the electromagnetic spectrum, meaning it cuts across different wavelengths. How is this even possible? That's because active galaxies have supermassive black holes at their centers. If you're not sure what a black hole is, that's just a region in space formed after an enormous star runs out of fuel and dies. It collapses on itself under its gravity, causing the gravitational pull to become so strong that nothing can escape it, not even light. The black hole at the center of active galaxies sucks in matter from their dense center. This process is referred to as accretion. As the matter is sucked in, it will form a spiraling disk that eventually heats up thanks to the forces of friction and gravity. Beams of highly energetic particles are produced and pushed out away from the disk at almost the speed of light. In quasars, everything scales up. They are also formed when these active galaxies crash into one another, driving their masses into their supermassive central black holes. Usually, the matter consumed by these black holes is made up of insane amounts of gas. As it falls in, the inner parts of the black hole orbit faster, creating the friction and the heat we mentioned earlier. Combine this with the ejection of beams of highly energetic particles, and you'll have a nucleus so luminous that it becomes visible to distant universes. The existence of quasars challenges several things we thought we knew about the early universe. For one, the fact that they exist just a few 100 million years tells us that they formed really quickly. It also means that galaxies form and evolve much faster than we previously thought. According to scientists, the high redshifts of these cosmic mysteries tell us that we're seeing them as they were when the universe was much younger. Now that upends everything we thought we knew about the expansion of the cosmos. What else is there to these mighty yet mysterious beams of light emanating from billions of light years away, yet visible to even amateur telescopes? How powerful are these cosmic wonders, now considered the universe's ultimate fireworks show? If quasars are as far away as astronomers say they are, it's notable that we can see the light they produce all the way from there. For instance, the quasar 3C273, the first quasar ever to be identified, is 2.5 billion light-years away. It was discovered in the early 60s by astronomer Alan Sandage and is still visible today. There's only one explanation. They are just that powerful. In fact, when curious scientists first set out to calculate the energy output of quasars, their minds could not accommodate the possibility of anything emitting that much energy. The luminosity of the quasar 3C273 has been estimated to be about 2.5 C1040 watts. For context, the Sun has a luminosity of 3.9 x 1026 watts. That means that this particular quasar shines as bright as 25 trillion suns. Of course, it makes sense that those scientists just couldn't comprehend their calculations. Now let's see how quasars compare to galaxies in terms of power output. Our solar system is in the Milky Way, which contains about 100 to 400 billion stars, including the Sun. Yet, our galaxy only produces energy of about 5 x 1036 watts. Just one quasar can emit up to 1040 watts, which is far more than hundreds of galaxies may be able to churn out combined. Let's bring that home. Such massive energy output by quasars means just one can be up to 100,000 times more powerful than all the energy output of the Milky Way. Mind-blowing, isn't it? Well, there's more. Due to the extreme nature of the forces involved in the creation of a quasar, they can emit radiation across the electromagnetic spectrum. This means we can study their properties in different ways and with different types of telescopes. In addition, further research has shown that these quasars have the ability to also influence their host galaxies through a concept known as quasar feedback. It affects the rate of formation of stars and, in turn, the long-term evolution of the galaxy. Quasars sure seem fascinating enough, but what about pulsars? What is it about them that has got the world talking for decades? In the vast ocean of the universe, pulsars stand out as lighthouses, emitting light beams that sweep across it in a circular motion. They are rapidly rotating neutron stars with magnetic fields so strong that it influences the motion of their light beams. Although pulsars and quasars sound alike, they're quite different. Pulsar is short for pulsating radio source, a name given based on how they were first discovered. Jocelyn Bell, a graduate student at the University of Cambridge, first detected the signals they produced back in 1967 with a radio telescope she had built with her supervisor, Anthony Hewish. At first, they thought it was simply radio interference, but they soon observed that these signals were recorded as regular, repeating pulses of radio waves, occurring every 1.337 seconds. The consistency of these signals was too significant to ignore, because there was no prior similar observation in astronomy. Had humans finally detected another civilization? Were these pulses produced by the aliens we all believe exist? Jocelyn and Anthony certainly considered it, even going as far as naming the signal LGM-1, meaning Little Green Men. If you're familiar with the depictions of aliens in movies and literature, you'd get the drift. Why didn't that hypothesis last? Well, another pulsating source was soon discovered. this time located in a different direction from the previous one. Since then, more than 3,300 pulsars of different types have been discovered. These celestial objects now serve as evidence for the existence of neutron stars, first proposed by Walter Baade and Fritz Zwicky in 1934. What are neutron stars anyway? Just like quasars, they're the result of catastrophic events, this time involving a supergiant star. We now know that stars aren't merely shiny objects somewhere far away in the universe. They're massive luminous bodies of hot gas held together by self-gravity. We also know that stars don't shine, or more accurately, burn forever. The events that follow the death of a star depend on its size. However, they generally run out of hydrogen, which powers them at their cores. Bigger stars take things a step further by fusing heavier elements like helium within their cores. As you might imagine, this creates large amounts of energy and pressure, balancing the tendency for gravity to pull matter and causing the core to collapse. 4 celestial objects can be formed after the death of a star, depending on its size: a red supergiant, a planetary nebula, a neutron star, or a black hole. Most neutron stars are formed by the death of a star up to 20 times more massive than the Sun, but not massive enough to form a black hole. When the core of such a star collapses, every proton and electron is crushed together to form a neutron, but the resulting neutrons can stop further collapse that would form the black hole. Because they were first stars, neutron stars are littered across the galaxy. NASA says there are up to 1 billion of them in the Milky Way galaxy alone. However, some become undetectable over time because they no longer generate electromagnetic radiation strong enough to be detected here on Earth. This is where pulsars stand out. You know what else is outstanding about these mysterious objects? Their unfathomable speeds. How is it possible that the weightiest object in the universe is also the one with the highest rotational speed? The easiest way to grasp the rotational speed of pulsars is to think of ice skaters. Have you noticed that when they want to do that insane move where they spin rapidly, they draw their arms in? Pulsars follow the same principle, which is called the conservation of angular momentum. The stars from which they form have some level of angular momentum that causes them to rotate. Now, as the core of a star collapses during death, its size also reduces drastically from thousands of kilometers to about 10 or 20. Like the ice skater who spins faster when they pull their arms in, the angular momentum of the star increases rapidly as its radius reduces. This is called the law of angular momentum. Their unfathomable speed begins to make sense when you consider just how dense they are. The material that forms a neutron star like a pulsar is so dense, just 1 teaspoon of it would weigh 4 billion tons. With such a compact center, the pulsar will be able to maintain its speed. The fastest pulsar astronomers know in the Milky Way was discovered in 2022 and is called the Black Widow pulsar. It is also designated PSR J09520607 and has a mass about 2.35 times that of the Sun. Its speed? 707 hertz, meaning it spins 707 times per second. The pulsar PSR J17482446 AD is the overall fastest though, reaching speeds of 716 hertz. One interesting thing to consider when describing the power of pulsars is their ability to recycle. Here's what we mean. Sometimes one cloud of gas can birth 2 massive stars that end up being close to each other. They form a binary system and begin to orbit each other. Again, their fate depends on their sizes. However, there are 2 possible results of the supernova explosion of these stars. One is for the explosion of one star to blast the other out of the system. The second possibility is that the explosion of the more massive star leads to the formation of a neutron star, and the system remains intact. Or does it? If the neutron star in a binary system is a pulsar, it will also spin at high speeds. Over time, its energy depletes, and so does its speed. This is where the second star comes in. The pulsar can suck in material and energy from its twin star to rejuvenate it and increase its spin speed once again. In case you were wondering, this is how the Black Widow pulsar got its name. Black widows are a species of spiders known to feast on their mates. Another thing that happens when a pulsar becomes part of a binary system is the creation of gravitational waves. These ripples in space-time are produced when massive objects like neutron stars accelerate asymmetrically. The waves generated travel at the speed of light across long distances and can be detected using specialized sensitive instruments like the Laser Interferometer Gravitational Wave Observatory, LIGO. We've talked about the extremely violent conditions that birthed pulsars and their zombie tendencies, but what produced the pulses that made Jocelyn and Anthony detect them in the first place? To talk about that, we must talk about the incredibly strong magnetic fields of pulsars. It's a big deal because they're among the most magnetic objects in the universe, and this affects their behavior. Physicists have described pulsars as giant permanent magnets with two poles. They emit radiation from these magnetic poles, but their magnetic axes are misaligned with their rotational axes. Consequently, they sweep through space as the pulsars spin. The beams of electromagnetic radiation formed are due to the acceleration of charged particles under the influence of the strong magnetic field. These beams of radiation are emitted along the poles, but because of the misalignment we talked about earlier, they sweep through space. The result? Just like you can only see the light from a lighthouse when it points in your direction, only beams pointing towards Earth can be detected. Otherwise, we'd have nothing. And that's where the pulse comes from, even though the pulsar is constantly emitting radiation. Having taken a brief look at quasars and pulsars, here's the next big question to answer. Which one is the true cosmic icon? What else do they have in common, apart from their similar names? What are the differences that make each one stand out? Quasars and pulsars are fundamentally different celestial objects. Quasars, as we already pointed out, are also known as active galactic nuclei, AGN, whose emissions are powered by supermassive black holes at the centers of active galaxies. Pulsars, on the other hand, are simply neutron stars, highly dense remnants of massive stars. A notable distinguishing factor between both cosmic giants is size. Crossing from one side of a quasar to the next has been estimated to take just a few light days. Compared to galaxies and other galactic phenomena, that's quite small. But when you bring pulsars into the conversation, it's a whole new ball game. The extremely dense neutron stars have a diameter that typically does not exceed 20 km. New York City's Manhattan is said to be about 21 kilometers, so a pulsar would fit within its length and even leave some wiggle room. Now, quasars and pulsars are both luminous celestial objects located light years away from the Earth, but the brightness of pulsars pales in comparison to quasars. Quasars are said to outshine entire galaxies by miles, despite being millions of light years away from us. We have pulsars within our Milky Way galaxy, but their luminosity isn't what drew us to them. You know what is impressive about them, though? Their rotational speeds. While some rotation is involved in the activity of quasars, it's nothing compared to what astronomers observe with pulsars. In fact, a quasar that spins up to 1/3 the the speed of light is considered uber fast. That's like child's play for pulsars, which can spin up to 716 times in 1 second. How do quasars and pulsars compare in terms of energy generation? At this point, the answer seems obvious, but let's break it down for you. The accretion of matter onto a supermassive black hole powers quasars. This process can produce a total power output of up to 1,040 watts and the emission of radiation across the entire electromagnetic spectrum and in all directions. Pulsars are only able to generate energy due to their rapid rotation and strong magnetic field. Their energy output has been estimated to be between 1,025 and 1,028 watts, and most of their radiation beams are detected as radio waves. Furthermore, the detection of the radio waves only happens when they point directly towards Earth. Let's just say the quasar is the bigger giant in this case too. Let's now consider who has the biggest impact in cosmic space. So far, scientists have been able to ascertain that pulsars only have a local impact by affecting nearby stars and planets. Their strong magnetic fields barely have any effect beyond the galaxy where they're situated. As expected, quasars have a much larger impact, and this is explained by the concept of quasar feedback. Radiation from quasars tends to affect their host galaxy. They produce powerful outflows of ionized gas that can either trigger gigantic starbursts or heat up the interstellar medium such that star formation is halted. In a nutshell, quasars can affect the evolution of galaxies by interfering with star formation. What do all these mean for the universe? Why is it important for astronomers to study these cosmic phenomena that seem so far out of reach? How can they affect our world as we know it? We're all fascinated by the origins of our world. What happened in the past? How did we get here? It feels like part of our cosmic responsibility to learn as much as we can, not just about our planet, but the universe we find ourselves in. This is why studying things like quasars and pulsars is relevant. While we continue to probe to see what big thing lies ahead, here's what we know. Quasars help us to understand the formation and evolution of galaxies. Processes like accretion, star formation, or its inhibition via quasar feedback provide information on how galactic evolution takes place. Astronomers also use these galactic powerhouses to unveil the universe's structure. Pulsars are even more fascinating because of how they serve as natural laboratories for testing laws of physics. By interacting with pulsars, scientists can learn more about the life cycles of stars and how this impacts the chemical balance of galaxies over time. They've also discovered that pulsars can be used to test Albert Einstein's theory of general relativity, especially under such extreme conditions. We can learn how matter behaves under different conditions, such as the high densities and strong magnetic fields that can only be found on pulsars. For some astronomers, what's most intriguing about pulsars is their ability to serve as cosmic lighthouses. This will help with the navigation of the universe, as the periodicity of their signals can be used to determine the location of spacecraft in deep space. Others are interested in the use of pulsars as gravitational wave detectors. The detection of such waves informs us of cosmic events like black hole mergers, supernovae explosions, and gamma-ray bursts. Man's curiosity on Earth has led us on a path towards technological advancements for better, healthier lives. Learning about our universe and the deep mysteries it holds has the potential to lead us towards even more. What has this got to do with quasars and pulsars? Everything. How so? The universe is a mighty expanse of mysteries that has captured the attention of astronomers right from the days of Aristotle and Galen. We've come a long way since then, going as far as unveiling the existence of quasars and pulsars. However, this isn't just about fascination. These awe-inspiring cosmic beacons are advancing our knowledge of the cosmos as we continue to seek to map out our universe and understand the world around us better. By prying deeper into the wealth of information they offer, we can learn about our origins and what the future looks like. Studies are being done to understand events like the rapid growth of black holes, how quasar feedback works and affects the universe at large, and how these affect matter distribution in the cosmos. Pulsars are being used to learn more about neutron stars and to search for the existence of pulsar planets and exoplanets. We know how matter behaves within our limits. What happens when these limits are taken off? What happens when extreme conditions, like those birthing quasars and pulsars, kick in? That's where we're headed, but it's only the beginning of our grand adventure. What's the most captivating thing about all these for you? Drop it in the comments section. Let's rub minds together. Don't forget to like this video and subscribe to this channel if you haven't. We've got several other exciting videos in the works that you wouldn't want to miss. You can also share with your friends and family who love astronomy as much as we do. See you next time.